Hello, everyone. My name is Manoj Sakya, and I'm your host today in this SLS Talk series. And this SLS Talk series is organized by uh, SCSE-GSC club. And today we are having our friend, his name is Lyuye Zhang. And without further delay, I would like to welcome Lyuye Zhang. Thank you so much for accepting our invitation, Chan. And today is episode number 23. And let me give a brief introduction about him. Lyuye Zhang is a third-year PhD student, and he completed his bachelor's from Ghent University. He did his master's of engineering from Nanyang Technological University itself, and currently a PhD third-year student. And he has published several papers and has won certain very important awards, distinguished awards as well. And without further ado, let me hand over this mic to my friend Lyuye Zhang. Lyuye Zhang, you can share the screen and you can start the presentation. And today the title of the presentation is Beyond Signatures: Incompatibility Detection at Semantic Level for Java Third-Party Libraries in Open Source Ecosystem. Lyuye Zhang, you can start the presentation. And if audience, if you have any questions, maybe you can ask at the end of the presentation. But for now, during the presentation, please mute yourself. Thank you very much. Lyuye Zhang?
Okay, thank you, Manoj.
Yeah. Let me give you, make you a co-host. Yes, here you go.
Okay, thank you for inviting me. My name is Lyuye Zhang from Cybersecurity Lab. My topic today is about the incompatibility detection. Sorry.
Yeah, please go ahead.
Okay. The incompatibility detection at semantic level for the Java library. This topic is a subfield of the governance of open source ecosystem and the software supply chain. So it's basically based on the software engineering. Let's start with some background. As we all know that software applications are everywhere nowadays, like the websites or mobile apps or even IoT systems. But actually, all of this, most of the software we use nowadays, they actually use the open source software. So we can see from this chart, from 2016, there are on average 84 open source components per app, be increased to over 500 at 2020. So it's like increased 259% over 5 years. So you can see the usage of open source software is boosting. In nowadays, there are 60 to 90% proportion of the in development software they use this open source software code. It can be predicted that till 2026 there will be 300 million open source software repos at that time. So we can see the usage of this open source software is really boosting, and lots of developers, they choose to use this open source software when they develop their own projects, because they don't really have to reinvent the wheel, and they can reuse the existing implementations. But how do they really use these softwares? Let's take example here. Let's take the Node 1 as your own in development root projects. You For example, if you use three third-party libraries on as your dependencies, they are denoted as blue nodes here, and actually these libraries, they use other third-party libraries, their own dependencies. So in fact, you would use like these green nodes and red nodes, you would indirectly use the other libraries that you didn't choose to use as your own dependencies, but they're called indirect dependencies. So all the dependencies altogether, they form the dependency graph to make your direct dependencies function properly. And this OSS open source software, they're called third-party libraries. And all these third-party libraries, most of them, they depend on each other. So this interconnected OSS, they form a huge graph altogether. So when you want to use some dependencies or use some libraries from it, you may want to ask the package manager. For example, for Java, most popular package manager is Maven, and they will retrieve some your libraries for you, and also the indirect dependencies. So a subgraph or a local subgraph for your own project will be retrieved from this huge dependency graph to for your own project. And there are also other package manager, popular package managers. For example, like for JavaScript, it's npm. For Python, it's called Py. Well, actually, when you use the library for your own projects, the libraries are not just single library. They actually have lots of versions. For example, a third-party library here, you can have a version from 1.1.0 to 1.0.3 in a sequentially upgrade. And sometimes when you use the third-party library, you may want to upgrade this from the lower version to upper version, because, for example, if the lower version has some vulnerabilities, you may want to upgrade. The upper version, new version has some new features, or some bugs have been fixed. You may want to upgrade to newer version. But however, when you upgrade new version, you may face a new problem. For example, here, if you want to upgrade from version 1 to version 2, that can usually be incompatible, so barely be compatible. But if you upgrade 1.0.0 to 1.1.0, they could possibly be compatible, sometimes are not, sometimes may be compatible. So to handle this kind of situation, Maven or as an open source community, they propose a semantic versioning rules to define this, to help guide the developers when they release a new version. They want to help guide them to release the correct version number. So they define these 3 digits to to denote the meaning of the upgrade. So for example, from the last digit is if you only the bug fixes are including in this upgrade, it's supposed to be compatible because it's just fix and bug. You may want just to upgrade the last digit, but second digits can accommodate some new functionalities, but still have to be compatible. And the first digit from version 1 to version 2 is called the major version. Any change can be allowed, including the incompatible change. So according to the semantic versioning rules here, like we only allow the patch upgrades, the first one, and the minor upgrades to be compatible. A third one can be incompatible. And speaking of the incompatibility, actually it also means introduce some breaking change here. So we want to introduce more about the breaking change. There are generally 2 types of breaking change. The first one is more primitive one. It's called syntactic breaking. It's based on signatures of APIs. For example, if you want to use the old version of the library, it's called the old method, but it's new version is changed to a new method. The signature has been changed. So when you still call the old method, it would be raise an error of like no such method found, or like this kind of errors. This is a pretty lower level breaking chance can be easily detected by the API checkers. But there are beyond these signatures, there are some semantic breaking. It doesn't violate the signature rules. It can only be detected by the unit test because the combination would be successful after the upgrade, but the behavior is not same. So the results generated by the program may not be different, maybe different. So there will be no rules to detect such kind of different behaviors. So that is why we want to develop a tool to help detect such kind of semantic breaking change. Here's a motivation here. The motivating example. In this example, we can see this code diff here, including the previous version and the newer version. This is code snippet of the function, and the function itself, the signature remains same in the new version, but the code content is changed. You can see here in the first, second line, third line, is the old condition. The old code includes if conditions, 3 if conditions, but in the newer version is changed to the first condition remains same, but the second and third has been changed to a while loop, and also a condition to break this loop. And because of this if condition to the while loop condition, it introduced a potential while infinite loop here. Because under some certain input, the program may not exit correctly and will cause infinite loop here. And this does not violate the signature. So if the combination will be successful, but the result will be different. Like here, the infinite loop is occurred. So because of this kind of problems, and current API checkers, existing tools cannot detect this kind of semantic breaking. And even if the unit test can detect it, it still be limited by its coverage. So we all know that the unit test cannot cover all the APIs, all the code. Usually just cover some critical APIs, and also cannot cover all possible inputs. So that's why we have to use we have to develop a new static tool to detect such semantic breaking efficiently. To detect such kind of semantic breaking tool, that we have to first investigate what kind of chance would cause this kind of semantic breaking. So we collect 180 real world cases, and we manually go through them to figure out what's the root cause of this. And we can see that 73% are caused by the execution logic change. For example, like the if statement change, like the previous example, the if statement change has changed to while loop. So the execution logic has been changed. It could go to another branch in the new version. So, but this can be captured by the control dependencies. And then another segment cause is the calculation change. For example, from A+1 to A+2, the A value of A would definitely be changed because of this code change. But this can be captured by the data dependencies. And some of the cases, but most of the cases are have both of these changes, so the neighbors can overlap with each other. But with this, the cost is not enough to detect the semantic breaking, because if we only use the patterns we found before, we will generate lots of false alarms. That's why we had to find some what kind of chance that will not cause a semantic breaking. So we collect some successful test cases with backward level change. That means these cases have changes, but it does not cause the semantic breaking. So we summarize these cases to these categories. The primary category is the benign changes. It means that the new version does change the behaviors, but it changes the behavior in a good way. For example, it just fixes bug. The users wouldn't be care of this kind of change because it doesn't really affect the normal usage. That is why we had to rule out this kind of change to make sure this won't be reported as a false alarm. there are also other categories of good changes that we want to rule out. Since the benign change is the primary one, we just introduce them more. As I mentioned before, the bug fixes are allowed in the patch upgrades. It should be backward compatible. So we want to find out these bug fix patterns to identify them and try to rule out them during the detection to make sure we won't report these bug fixes. So first we summarize some patterns for bug fixes, and also the new functionalities. They are also listed here, and we want to de-emphasize these benign changes during the semantic calculation. Here goes the methodology. It's an overview of the tool. Our tool is called Semantic Breaking Issue Detectors, abbreviation is SEMBIT. The tool is based on, it will detect the semantic breaking based on the API pairs. Because the API itself are not changed in the new version because the thing should remain same. But the API, the methods called by the API are changed. That is why we want to first find the API pairs from the old version first and the new versions for the API 2 pairs. And first step, we want to generate the call graph for both of these APIs because the API itself may be the same, but the method called by the API could be changed, and this would change the API's behaviors indirectly. But we still want to detect such kind of inconsistency. And then we want to group the changed methods all together as clusters to mitigate the effect of refactoring, because refactoring also should not be reported because refactoring doesn't really change the behavior, so it won't generate any different output. And when we get these clusters, we want to backward slice the output because we want to focus on the outputs. We don't want the output to be changed. To get the control dependencies, as mentioned before, they can capture the execution logic change, and also the data dependency slicing to get the data dependencies. And also, because a new exceptions would also crash the user's project because there's some new exception cannot be captured by the old code. As well, we also want to locate the new exceptions. With all this, we want to construct the semantic graph based on the control flow graph and all these dependencies annotated by the dependencies. Eventually, we want to calculate the semantic diff with this WL algorithm. This algorithm is commonly used by code clone detection to capture the semantic difference between the two code to abstracted code. If we capture the semantic change in this diff, we can consider these clusters because there will be group of clusters, bunch of clusters under the API. So we capture this cluster, they have a breaking change, but we cannot sure it will affect the API. So we want to further check the triggerability. If it's triggerable from the API, also the output can be propagated back to the output of the API to really affect the output of the API. If both of these cases stand, then we consider the semantic breaking is captured. I take a brief example for this methodology, and this is an example of the motivating example. Motivating example. The first one can extract the control flow graph, and then we annotate the control dependencies and data dependencies here. And further, we want to construct the semantic graph based on this Westphal-Lemon algorithm and calculate the semantic difference. And during the calculation, we would identify the benign change patterns we found before to assign them with lower weights to de-emphasize them and in the final results. And as the final result, we want to calculate similarity with this formula. And if this formula is above threshold, then we think the semantic breaking here is captured in these clusters. And if it's captured, then we want check if it can affect the API's output. First, we want to check if it can be triggerable from the input along the call chain in the call graph. If the output can propagate back with a feasible chain back to the API's output, then we consider the semantic breaking is captured in this cluster. But for this cluster, because it only transits a debug information which will not be output by the API, we wouldn't report such case as the semantic breaking. To evaluate our tools, we construct a benchmark dataset because there's no such dataset available for the semantic breaking chain. So we first construct a dataset, and then we collect some other tools. And since there are also no other tools available, no non-static tools available, so we just collect some API checkers. And to further evaluate the ability of our tools regarding the false alarm reduction, we develop another baseline tool which consider all the backcode change as semantic breaking, which means this baseline tool can be pretty sensitive. That's why it has very high recall here on second line baseline tool, because it takes all the backcode changes of semantic breaking. Of course, it will report all the changes, but it has very much lower precision because it cannot identify the false alarm, and which proves that our tool is able to identify the false alarm and will not report such kind of false positive cases. And we also want to compare with unit tests, because unit tests are common practice to detect such kind of semantic breaking. And since the unit tests are developed by the developers themselves, they cannot cover all the APIs. That's why we can see in this chart, unit test doesn't test 83% of the APIs. They can only cover the rest, 16%. We can see that in the ground truth, it has 2% APIs labeled as semantic breaking API, but the unit test can only find 0.4%. And our tool, although our tool will produce some of false alarms with 2.3%, but the general performance is pretty acceptable because you can cover all the tests, all the APIs, because it's a static tool, which doesn't require the user specified input. And last, we also try to evaluate this semantic breaking prevalence in the Maven ecosystem, because as I mentioned before, when you use your own dependency graph, that's a subgraph for your local projects. But the Maven ecosystem has like millions of graphs libraries there. We want to evaluate the prevalence of the semantic breaking in the entire Maven ecosystem. But first, we just sample the popular ones. And this, as we can see here at the left, we show the minor upgrades, and the right is the patch upgrades. We can see the minor upgrades are more likely to be breaking than the patch upgrades, because it's some people may find the minor upgrades to be incompatible, to be acceptable, but the patch upgrades should always be patched backward compatible. But we can see from this chart is that the gray and the blue are the syntactic breaking. So beyond this syntactic breaking, we can also find lots of semantic breaking in the ecosystem. But since they are not easily to be detected, they can jeopardize the user's projects and unexpectedly, because no such useful, effective tool can detect such semantic breaking. So that is why our tool is able to review such kind of cases to help users upgrade it safely. Okay, that's all for my presentation. Thank you for your attention.
Thank you so much. It was really an interesting topic. I really liked it. But why? Let me quickly ask a question, because audience, they will ask pretty soon. And to all the audience, if you have any queries, either you can unmute yourself and ask a question, or you can write a question in the chat box. So so I can read it out. Lyuye, first question, let me go ahead. Why your title says like Java third-party libraries, right? So
Yeah.
so your experiments, they were only related to Java third-party libraries, or is there any specific reason you mentioned that part?
Okay. Okay. My focus is about the Java library only because because in the Maven ecosystem, which is a most popular repository for Java libraries, because it's a pretty old ecosystem, it's like have decades of years, and that's why it doesn't really I mean obey the semantic versioning rules. So for example, like we found before, the patch version and the patch upgrades and minor upgrades, they should be compatible, but actually they are not. And this is also reviewed by other researchers about the syntactic breaking. So that's why I focus on this the ecosystem, because they are more vulnerable to the incompatible change.
Okay. So,
Because it's
but
pretty
your
old
study,
system.
yeah, but your
Yeah.
study should be applicable to any kind of languages, right?
But actually, these two only can handle the Java language. So probably in the
Oh,
future, we can
okay.
develop more tools for other languages as well. But
More
the
generalized
theory
one.
is the same. Yeah.
Why is it like restricted to only Java? Why not to other languages? Is there any reason why it only works for Java third party?
Um, um, okay. Actually, because all the language is based on a static analysis, right? And the static analysis, I mean this analysis tools are very different for each language, so I can't really just
Okay,
apply
okay,
this tool to other
okay.
languages. So I want to use some other tool and may
Right,
have because they're pretty different. And Java is a static type.
right. I agree. I agree. Yeah, thanks. Participants have not put any questions so far. We are waiting for your questions from the participants. So let me continue asking few other questions because it's really interesting. I really enjoyed your talk basically. So what I like the way in your presentation is you started from the very right beginning. You know, what are a patch version, and then you know, those minor versions, and then major revisions and all those things, and then finally you came with a very motivational factor. So I was thinking, like, when you had the diagram with the you know, older version and the new version, and then they go to the next level in the like a call graph or something like that.
Yeah. Yes.
So I want to know a little bit about that part before this slide. I think yes, something like that. Yeah, in the methodology. In the methodology.
Sorry.
No, not this one. Methodology.
You mean?
No, methodology section.
Oh, okay. Yes.
You know the major,
Excuse me.
yeah, major diagram. I think the main diagram.
You mean the
I
overview?
think, yeah, yes, this one, this overview. So I think this is this diagram basically represents how same bid actually works, right? If I'm not wrong.
Yes. Exactly.
Yeah. So I was thinking, like, how these graphs are generated. Is it like basically the way how it should work, or it is up to you to design the graph? You know, you generate the call graph in the first place. What is
Okay,
the importance of having that one? Yeah.
it's actually it's kind of pretty straightforward for Java to generate the Java call graph. It's just use the existing tool because first we have the older version and the newer version because we
New
have the
version.
bytecode of the published library, right?
Okay.
So the published library has a complete bytecode, so we just read the bytecode to generate the call graph, static call graph, without any dynamic input like that. It's kind of pretty straightforward.
Okay, so basically, with the generation of the call graph, so you have two different graphs from the two different versions.
Yeah.
So from those graphs, you have this derived dependencies and all those things there, right? So here in the 4.2.
Actually, okay, we want to, this is work only focus on, we want to determine for one library, two variants, okay, two variants of one library. Between these two variants, actually it's just for one library, right? So there will be only, so there will be no other libraries. This is just for one library. Then we want to find out in this one library, how many APIs have semantic breaking.
Okay. Yeah. So this is only for one library case.
Yes.
So okay.
So if the user want to use this to detect the semantic breaking API, you may want to use this between the two versions of each of these their dependencies. So that have 10 dependencies, and the 10 dependencies have 10 pairs. So it just runs 10 times like that.
Oh, okay. Good. Yeah. Thank you, Lyuye. Thank you so much. I think this is not my area. That's why I'm actually asking a lot of questions, but very interesting because I like programming, and then the structure of the programming is really interesting. So my last question, I think, how this research will be affecting in the field of OSS.
Okay. Okay, as I mentioned on this last RQ, a moment. Okay, here. Because there's no too effective static tool to detect such kind of breaking here currently, right? So, but the breaking chance, they do exist in the stack system. So if you don't know their existence and you just simply upgrade because it compile well, the compilation works, and you just upgrade, and it will, I mean, like crash your project or generate just different results unexpectedly. That's the that's the danger of the semantic breaking. That's why we have to just detect them before they are deployed. Yeah.
I agree that. So in that perspective, your study could be very, very helpful to all the developers, I think. Basically.
Hopefully.
Yeah. So Lyuye, thank you so much. It was really an interesting topic, and I really enjoyed your presentation throughout. And I also like to thank all the participants who joined this SLS Talk episode 23. And I hope they all actually enjoyed your presentation, Lyuye. I wish you good luck for the future. And
thank you.
We'll definitely come up with next episode. And till then, I would like to say goodbye to everyone. Have a good day. And thank you so much. Lyuye, thank you once again. Thank you so much. We'll upload this episode in our YouTube channel very shortly. And yeah, thanks a lot. Lyuye, thank you so much.
Thank you.
Yeah. Yep. Okay. Bye bye. Bye bye. Take care.
Bye.
Take care, everyone. Thank you so much.